Hello and welcome to tutorial number 4. Our topic today is the periodic table, isotopes, and electron configuration. Before we get started with that, just want to give you a quick reminder that the notes are available from my website to accompany each and every tutorial video, and I do highly recommend that you have those in front of you as you go through these tutorials. All right, with that said, let's get started with the periodic table. And you can see I have a periodic table over here. I'm going to zoom into that and we're going to look at the periodic table as a whole. But before we do that, let's just pull out one little block for one little element and look at the information that's contained in each block. So let's just pull out hydrogen here. So just copy down what you see in the periodic table. Okay, so it's always going to start with a whole number on top. And then we have the element symbol. If you're lucky, you'll have the element name as well. I've written out the element names for all the main group elements here. And then on the very bottom, you're going to have a number that is not a whole number. That's 1.01 for hydrogen. Okay, so I just copied everything that you're going to find in the block for hydrogen. So what do these numbers and symbols mean? Well, the first number, the whole number, is your atomic number. So I'm going to label that. Atomic number. Sometimes symbolized as Z, capital Z. So I'm going to write a capital Z there. And the atomic number is always going to be equal to the number of protons in the nucleus for that element. Okay. All right, next we have the element symbol. And not all periodic tables are going to have the full name written out for you. I went ahead and wrote it in for the main group elements for the periodic table that you have on slide number 3. So this is the full name, but don't rely on that because not all periodic tables are going to have that. And then last but not least, this number is not going to be a whole number because it is a weighted average for all the naturally occurring isotopes of that particular element. So it is not going to be a whole number. It's a weighted average, and it's called the atomic mass. Okay, and the atomic mass, again, let's say one more time, it's good to have repetition. That is going to be the weighted average for all the naturally occurring isotopes of that element. And if you don't know what an isotope is, don't worry, we're going to talk about that a little later in this session. Okay, but the unit, because it's just the average mass of one atom, it's a very tiny unit. It's AMUs, atomic mass unit. So I'm going to write that there, AMU, atomic mass unit. So it's good to know how the atomic mass unit relates to the gram. One atomic mass unit is equal to 1.660539 times 10 to the negative 24 grams. Okay, so if you ever need to do a conversion between AMUs and grams, there's your conversion factor right there. And AMU is very, very tiny, because it's used to represent the mass of just a single atom of an element, which is a very tiny, tiny particle. Okay. All right, so I'm going to erase all this and we're going to zoom in to the periodic table and look at the periodic table as a whole now. Okay, so when looking at your periodic table, these vertical columns, these are referred to as your groups. And I'm just going to really focus in on the main group elements, which include group 1A, 2A, jump over here to 3A, 4A, 5A, 6A, 7A, and 8A. Those are your main group elements. That's what you're going to focus on in an introductory chemistry class. And then we have our horizontal rows, which are called our periods, and you'll see that those are numbered. So this is period 1, period 2, period 3, period 4, and so on. So if you were referring to the element that resides in period 3, group 7A, we'd just look at period 3, group 7A, and we'd see that that is the element chlorine. Okay, so main group elements, that's going to be our focus in any introductory chemistry class. But then here we have our transition metals, not part of the main group, so you probably won't be dealing with those a whole lot. And then we have our inner transition metals pulled out at the bottom, pulled out from here. Okay. If we had these up here in the periodic table, our periodic table would be very wide and wouldn't fit very nicely on a sheet of paper. So those are pulled down here. Okay, also important to note is that your metals shown in this particular periodic table in yellow, so nice and color-coded for you, those are going to be the elements that are on the left and lower side. Your non-metals are color-coded in blue in this periodic table. Those are going to be the elements that are in the upper right of the periodic table. And then you'll notice, even if your periodic table is not in color, you should always have this sharp dividing line here between your metals and your non-metals. And around that dividing line, you'll have 6 metalloids. Mine are shown in green. If you don't have the colored periodic table, it might not be a bad idea to memorize these 6 so that you can tell which of these 6 around this dividing line are metalloids, not non-metals or metals, but have intermediate properties from both. And so that includes boron, silicon, germanium, arsenic, antimony, and tellurium. All right, now, last but not least, the elements that reside in the same group have very similar chemical and physical properties to one another. And so we often refer to them as by their collective name. And their collective name tells you a little bit about their reactivity. So for example, all of the elements in group 1A are called the alkali metals. All of the elements in group 2A are your alkaline earth metals. All of the elements in group 7A are referred to collectively as halogens, and all of the elements in group 8A are collectively referred to as the noble gases, so called because they are stable and unreactive, and they're typically found in their elemental form in nature, not combined as part of compounds. Okay, that's a good introduction to your periodic table. We're going to go ahead and move on, but do note that there's a lot more information in here. We just haven't gotten to it yet. There is so much information given in the periodic table, and all I'm doing here is giving you a brief introduction to some of that information. Okay, we are on slide 4, subatomic particles. And we talked a little bit about the subatomic particles back in tutorial 3. So I'm just going to quickly go through what we said in tutorial 3, and then we'll add to that information as well. So in tutorial 3, we said that the smallest piece of an element that can exist and still retain the properties of that element is called an atom. And we said that atoms are composed of the subatomic particles protons, neutrons, and electrons. A little dash there. Okay. We further said that the protons have a positive charge. Neutrons are neutral, so I'm going to indicate that with a 0, no charge. And electrons are negatively charged. Now those protons and neutrons have the majority of the mass. Protons are approximately 1 atomic mass unit. Neutrons are also about 1 atomic mass unit in mass. But the electrons are far, far less massive. I'm just going to write here significantly less than 1 AMU. In fact, their mass is so small that they're typically ignored. The mass of the electrons you can consider as being negligible. And we further said in tutorial 3 that the protons and neutrons reside in the dense central core of the atom called the nucleus. And outside of the nucleus, that's where you'll find the electrons zipping around in that much more voluminous area of the atom. So let's label that with a different color. Okay, so this is the nucleus, and it contains the protons. I'm just going to write P, and the neutrons, I'll just write N. Okay, and then outside of the nucleus, I'll indicate this area in green. In this more voluminous region of space, this is where the electrons, I'll just write E. Okay, be consistent there. Just write an E for the electrons. This is where the electrons will be found. Okay. All right, so let's talk about those subatomic particles in a little more detail now. I'm going to go ahead and erase this, and let's start with protons. Okay. Remember that the number of protons can be easily identified by just looking at the periodic table, because the atomic number of an element will tell you the number of protons in the nucleus for that element. So the number of protons is equal to the atomic number. Remember that that's sometimes symbolized as Z, a capital Z. So I'll write that there just to remind you. Now the number of protons is fundamental to the identity of an element. I'm going to write that here. Fundamental to the identity of an element. Okay, what I mean by that is that if someone is referring to the element with atomic number 2, okay, so I'll write Z equals 2. Okay, therefore 2 protons, right? 2 protons in the nucleus. They must be talking about one element and one element only. And you can check the periodic table to see which one has the atomic number 2. You'll find that it is helium. It must be helium. It can't be any other element. Helium is the only element that has the atomic number 2. Okay, so must be helium. Okay, and that's what I mean when I say that the number of protons, or the atomic number, is fundamental to the identity of an element. Okay, 2 different elements cannot share the same atomic number. That is, they cannot have the same number of protons in their nucleus. Okay, they would have to be identical to have the same number of protons in the nucleus. They can't be different. All right, let's go ahead and go on to electrons next. So I'm going to erase this. Okay, now the number of electrons will be equal to the number of protons if the atom is neutral, meaning it doesn't have an overall charge. Okay, so I'm going to write here, number of electrons will equal the number of protons in a neutral atom. Okay, so let me give you an example of that. All right, EX, for example. Na, that's the symbol for sodium. I know you wish it was S, but S is sulfur. Okay, so be very careful because a lot of the element symbols come from their Latin names, so they don't always have the symbol that you might wish they had. So this is sodium. This is a symbol for sodium. Notice that I'm not indicating any charge up here. Okay, so I'll write that in blue so it stands out a little bit more. No charge. That means that this is a neutral atom of sodium. So if we wanted to figure out how many protons and neutrons protons and electrons this neutral atom of sodium would have, we just need to look at the periodic table. Look up the atomic number, so find sodium, look up the atomic number, you'll see that it's 11. And because there's no charge, we know then that the number of electrons must also be 11. So think about that. What we're really saying is that there are 11 positively charged particles and 11 negatively charged particles. So overall the charge on the atom is 0. It's neutral. They would cancel out. Okay? Now electrons can be lost from an atom and electrons can be gained by an atom. So let's talk briefly about that here. Okay, so let's first talk about electrons being lost from an atom. If an atom loses electrons, then the number of protons is now going to be greater than the number of electrons. Okay? So you're going to have more positively charged particles than negatively charged particles, which means that overall the atom is going to obtain a positive charge. So I'm going to write that here. It's going to be positively charged. We call an atom that has lost electrons and obtained a positive charge a cation. Cation. Okay, a positively charged ion, a cation. So let's take a look at an example here. Let's say that sodium is now written with a 1+ charge here. So now the number of protons, still 11, because that's fundamental to the identity of the element, and the element is still sodium, okay? But the number of electrons decreased by 1. It has lost 1 electron. Let me write that here with the blue pen. Lost 1 electron, okay? So now the number of electrons is only 10. Okay, so we have 11 positively charged particles, 11 protons, only 10 negatively charged particles, only 10 electrons. So overall, we're going to have a 1+ charge. Lost 1 electron, left with a 1+ charge, indicated like so. All right, last but not least, electrons can be gained by an atom. Okay, so in this case, the number of protons would now be less than the number of electrons. Okay. So if there's more electrons, there's more negatively charged particles, then overall you're going to have a negative charge on that atom. Okay. We call an atom that has gained electrons and obtained a negative charge an anion. New terminology there. Okay, so let's look at an example of an atom that has gained an electron. And it can always be more than 1, but we'll just stick to 1 right now. So let's say that chlorine gains an electron and therefore obtains a 1- charge. So we're going to check the periodic table to figure out how many protons this ion would have. Okay, so just find chlorine. Find the atomic number. It's still chlorine, so it is still 17 protons. Number of protons doesn't change because it's still the same element. But now the number of electrons is not equal to the number of protons. There's going to be 1 more electron than protons. Let me label that here real quick before we go on. 1 more electron. All right, so now we have 18 electrons. That's 18 negatively charged particles and only 17 positively charged particles. So overall, a 1- charge. Okay, I'm going to erase all of this about electrons, and we're going to go on to neutrons. All right, so last but not least, neutrons. The number of neutrons can change without changing the identity of the substance. Okay, so can vary without changing identity of the element. We call atoms of the same element that have different number of neutrons and therefore different masses, because remember neutrons have a mass of 1 AMU, so the more neutrons in the atom, the heavier it's going to be. We call those atoms isotopes. So again, some new terminology today. Okay, so let's take a look at the way that we write the symbols for different isotopes, because this is going to be a really important thing when you get to the nuclear chemistry. Now, isotopes, they are going to have the same chemical and physical properties in basic chemical reactions, but when you get to nuclear chemistry, they're going to behave differently. Okay, so very important that you master the ability to write a correct symbol for different isotopes today. All right, let's take a look at carbon. So there are 3 naturally occurring isotopes of carbon. There's carbon 12, there's carbon 13, and there's carbon 14. And sometimes you'll just see it written as C12, C13, or C14. Okay, but we want to be able to write the correct symbol like we would write in a nuclear reaction. Okay, so for that, we're going to show a number called the mass number as a superscript in front of the element symbol. Okay, so let me label that number. This is called the mass number, sometimes abbreviated as A, and not to be confused with the atomic number, which is symbolized as Z, not A. Okay. And then we're going to write our atomic number as a subscript before the element symbol. So let's write in green here that this is the atomic number Z. All right, now the mass number is always going to be the sum of the protons and the neutrons in the nucleus of that isotope. Okay, so to figure out how many neutrons it has then, all you have to do is subtract the atomic number, number of protons, from the mass number, which is the sum of the protons and the neutrons. Then you'll know how many neutrons are in that isotope. Okay, so let's do that for carbon 12. All right, let's do it for protons, neutrons, and electrons. Will be good practice. So for the protons, you could just look at the periodic table, or if it's written here as a subscript, just look at the symbol. So the number of protons must be 6. It's always going to be 6 for carbon. It doesn't matter which isotope it is. That's fundamental to the identity of the element. Okay? Now the number of neutrons is found by subtracting the mass number, so that's 12, and the atomic number. So subtract the atomic number from the mass number, and you'll see that this particular isotope of carbon, carbon 12, has only 6 neutrons. Number of electrons, just for fun, we'll do that. We've written this as a neutral atom, and so it must be the same as the number of protons. 6 negatively charged electrons, 6 positively charged protons, therefore overall a neutral charge. Okay? Let's go ahead and do the same thing for carbon 13 and carbon 14. Okay? All right, so the number of protons, always going to be 6 for carbon. Doesn't matter what isotope of carbon it is, it's still carbon. So the number of protons and the atomic number, always going to be 6. Okay? The number of neutrons is going to vary though. So we have to look at the mass number. For this isotope of carbon, it's going to be 13 minus 6, or 7 neutrons. Number of electrons, just check to see if it's a neutral atom or if it's charged. This one's a neutral, that makes it easy. The number of electrons is equal to the number of protons. Last but not least, carbon 14. Okay, 6 protons. 14 minus 6, therefore 8 neutrons. And it's still a neutral atom, so the number of electrons is equal to the number of protons, and it is 6. Okay, so the heaviest isotope of carbon would be carbon-14. It has 6 protons and 8 neutrons in that dense central core known as the nucleus, whereas carbon-12 only has 6 protons and 6 neutrons, so this is going to be the lighter of the 3. Okay, so real quick before we go on, remember earlier that we said that the atomic mass given in the periodic table is the number that is not the whole number, because it is a weighted average for all the naturally occurring isotopes of that element. So now we can kind of start to see where that number comes from. So for carbon, that number is 12.011 AMUs. This is the atomic mass. Now in my periodic table, the atomic mass is rounded more because I didn't have that much room, because I made that myself. But if you look at a periodic table that goes out to a few more decimal places, you'll see that the atomic mass for carbon is a little bit over 12. Well, now that makes sense, because if we look at the 3 naturally occurring isotopes of carbon, we can see that there are heavier isotopes than just carbon-12. Now it's a weighted average. So 98.9% of all the carbon in the world, in your body and the food you eat, is carbon-12. Okay? So it's a weighted average, so you're going to account for the fact that almost 99% of the carbon is carbon-12 and has a mass of the carbon-12 isotopes. Okay? Just over 1% is carbon-13, and such a tiny, tiny trace amount, a very small fraction of a percent, is carbon-14. But there's enough of the carbon-13 and the carbon-14 to slightly bump up that weighted average so that it is a little bit over 12 AMUs. Okay? That's why it's not exactly 12, because it's not all carbon-12. There's also carbon-13 and carbon-14. Okay, we're going to erase all of this, and we're going to go on to our last slide, which is slide 5, titled Electron Configuration. Okay, so far we've just said that the electrons reside outside of the nucleus, but the location of the electrons is actually more specific than that. They are restricted to certain regions of space outside of the nucleus. Electrons reside in energy levels. Sometimes called shells, and these energy levels or shells are numbered. So there's an energy level number 1, 2, 3, and so on. Okay, and the higher the number goes, the further the energy level is away from the nucleus, so the further out it is. So let's just draw an example here. So here's our nucleus. Energy level number 1 would be closest to the nucleus, so I'll label that 1. 2 is further out. 3 is further still, and so on. Okay? And then within these energy levels, there are sublevels. And these sublevels are designated as either being S, P, D, or F. Now, in an introductory chemistry class, you're probably really only going to focus on the S and the Ps, because all of your main group elements have their valence electrons in the S and the P sublevels. So I'm going to circle those. All right, and then within these sublevels, there are orbitals. And an orbital is a region of space where an electron is most likely to be found. So I'm going to write that here, a region where electron is most likely to be found. Okay. And an orbital can hold 2 electrons max. That doesn't mean it has to have 2 electrons. An orbital can be empty with 0 electrons, it can be half full with just 1 electron, or it can be full with 2. Okay, so I'm going to write here 2 electrons max. in an orbital. Okay, so let's take a look at the shape of the S sublevel. And I'm going to go ahead and draw an X, Y, and a Z axis. Because we're thinking three-dimensionally here, the S sublevel has a spherical shape. Okay, so I'm going to draw a sphere here, a spherical shape. An S sublevel has just one orbital, that is one region of space where the electron or electrons are most likely to be found. So I'm going to write S sublevel, 2 electrons max, because it just has one orbital, that one region of space. The P sublevel, I'm going to draw the X, Y, and Z. And I'm going to draw it 3 times, okay, because your P sublevel is going to have 3 orbitals, one on the X, one on the Y, and one on the Z. So I'm going to erase this just so I have a little more room here. Okay. X, Y, Z. Okay. And those P sublevels have dumbbell-shaped orbitals. Okay, again, one on the X, so dumbbell shape. So I'll call this piece of X. One on the Y. I'll call it PZ. PY. Gotta pay attention here. PY, and then one on the Z. Okay, I'll call it PZ. Okay, so 3 orbitals in a P sublevel, and each orbital can hold 2 electrons max, so a maximum of 2, 4, 6 electrons in a P sublevel. So 6 electrons max, because there are 3 orbitals in a P sublevel. Okay? All right, so I'm going to go ahead and erase all of this. And next we're going to look at the periodic table, because all of this information for a particular element, location of the electrons, the electron configuration, is all written right into the periodic table. So you don't actually have to go memorizing a bunch of stuff, you just have to know how to read the electron configuration from the periodic table. So let me show you how to do that. All right, so we're going to consider the first 2 groups, okay, 1A and 2A, to be our placeholder for the S sublevel. We're going to call it our S block, okay? Now we're going to go ahead and pull helium over here, pretend that helium is here right next to hydrogen, so that it finishes off this nice rectangle shape, our S block, okay? And then what's left over here of the main group elements, groups 3A through 8A, with the exception of helium, remember it's pulled over here for this example, is going to represent our P block, okay? And then over here we see the numbers for our periods. Remember that those are the horizontal rows, and the numbers for our periods will represent our energy levels. Okay, so we have energy level 1, energy level 2, energy level 3, and so on. All right, so if we wanted to look at the location of the electrons in a neutral hydrogen atom, okay? Well, if it's a neutral hydrogen atom, we know that it's going to just have 1 electron to cancel out the 1 proton and give it a neutral charge, so 1 electron. So where is it? All right, so we're going to look at our periodic table and locate hydrogen, which just happens to be the first element here. We're in the first energy level, the S sublevel, and hydrogen is in the first column here. So just count it over 1. So there's just 1 electron in the first energy level, S sublevel. So let's draw that. Okay, so I'm going to draw a little blob for my nucleus. And then the first energy level, S sublevel, spherical in shape, closest energy level to the nucleus. And there's 1 electron in there, zipping around. And I'm going to just draw my electron as an arrow. Okay, let's do helium. A neutral atom of helium is going to have 2 electrons. Remember that we're going to pull helium over here to finish off our S block for electron configurations. Don't forget that. Okay, so if we want to figure out where those 2 electrons are in a helium atom, we would see that helium is in the first energy level. We're in the S sublevel, and helium is over 1, 2. So the 2 electrons are both in the first energy level, S sublevel. So let's draw that. So again, our nucleus, first energy level, S sublevel, spherical shape, 2 electrons. Now I'm going to draw 2 arrows. I'm going to draw them with opposite spin, but you don't have to worry about spin. That's just how we're going to do it for an introductory chemistry class. Okay, and then we're going to go on and do a lithium. Okay, lithium right here. So it's in the second energy level. Okay, so lithium is going to have 3 electrons. A neutral lithium atom has 3 electrons, and it's going to have some in the first and the second energy level. We know that because lithium is located in the second period. Okay. All right, so let's go ahead and draw the location of those 3 electrons. We're going to count all the way down to lithium. So starting up here, first energy level, S sublevel, we're counting through hydrogen and helium. So there are 2 electrons in the first energy level, S sublevel. So I'm going to draw 1, 2. And then in the second energy level, we're just going all the way down to lithium, still in the S block here. So second energy level, S sublevel, count over till you get to lithium. It's the first one. So in that second energy level, which is going to be a little further away from the nucleus, S sublevel, there's just 1 electron. So I'm going to put 1 arrow there. Okay, bear with me a little bit longer. I'm going to just do 1 more. I'm going to skip to carbon, which is right here. Atomic number 6. So if we're talking about a neutral atom, it's going to have 6 electrons. Where are they? Okay, so here's my nucleus. Starting up here, counting all the way down to carbon. Okay, so we start with some electrons in the first energy level, S sublevel. Check, check over hydrogen and helium. So it's first energy level, S sublevel, there are 2. 1 for the placeholder of hydrogen, 1 for the placeholder of helium. Keep going, you're going all the way to carbon. So now we're in the second energy level, also an S sublevel, counting over lithium and beryllium, we're going all the way to carbon. So the second energy level, S sublevel, is also filled with 2 electrons. So 1 up and 1 down, and keep going to carbon. Now we are still in the second energy level. We're still in period 2, but we're in the P block now. So in the second energy level, P sublevel, there are 1, 2. We get to carbon at 2. So there are 2 electrons. So I'm going to draw, that's going to be hard. I'm going to draw my P, okay, sublevel. 1 on the X, 1 on the Y, 1 on the Z. And I'm going to put 2 electrons, 1, 2. Doesn't matter too much where you put it, which orbitals you put it in. I just put it in 2 different ones. And you start to see that you kind of have to be an artist to do this. You can imagine trying to do this on an exam and thinking, boy, is this clear enough to my instructor? Is my artwork good enough? Well, fortunately for us, this is really just to kind of give you a better picture of the electron configuration. But as chemists, we're really going to write our electron configurations with letters and numbers. I just like to teach this first so that you have that visual of what the letters and numbers mean, okay? So I'm going to leave this up but I'm going to go ahead and write the letters and numbers, the electron configuration and the letters and numbers next to it so you can see how it relates. All right? So let's start with hydrogen. Okay. Hydrogen, we said, has 1 electron in the first energy level, S sublevel. So we're going to write 1s1. And what this means is the first number tells you what energy level. Okay. The letter tells you what sublevel. And then the superscript number at the end will tell you how many electrons are in that energy level and sublevel. How many electrons in that energy level / sublevel. Okay. All right, so let's do the same thing for helium. Okay, so we said helium has 2 electrons, both in the first energy level, which just has an S sublevel. So it's going to be 1s2. Okay. Lithium is 3 electrons. 2 of them are in the 1s, so 1s2, and then 1 is in the 2s, so 2s1. Okay, so let me go back to the periodic table, just so you see how we really get this from the periodic table. We're doing the electron configuration for lithium. We start all the way up here at hydrogen, we count all the way down to lithium. Okay, so hydrogen, first energy level, S block here. We're going to count it until we get to lithium. So 1, 2. Remember, helium is right here, so 1, 2. So that's where we get the 1s2. Go down to the second energy level, still in the S block. So 2s1, that's where we get to lithium. So we ended at 2s1. All right, we're skipping to carbon, okay? So starting all the way up at hydrogen, counting all the way down to carbon. All right, so starting in the first energy level, S sublevel, counting over through hydrogen and helium, which we're imagining to be here, okay? So 1s2. Go on to 2s. Count all the way through lithium and beryllium. You're still not to carbon yet, so you're going to keep going. So go ahead and write down your 2s2. The second energy level, S sublevel, is full with 2. Now we're over in the P block, still in the second energy level. So 2p, count until you get to carbon, 1, 2. So 2p2. So 1s2, 2s2, 2p2. Okay, for the electron configuration of carbon. All right, so I'm going to erase this here. Okay, so you might be wondering why this is really that important. Do you really need to be able to write electron configurations? Do you really need to know the exact location, or these distinct locations that the electrons take outside of the nucleus? Well, it turns out that the electrons are really the doers in your chemical reactions. Atoms will share electrons or transfer electrons to form different chemical compounds. Specifically, they're outermost electrons, the electrons in the outermost energy level, which we call the valence electrons. And so understanding the electron configuration of an atom will really help you to understand the chemistry that that atom is going to undergo. Okay, the reactivity. So yes, it is important. All right, so let me show you what I mean by that. Let's take a look at all of our noble gases. Noble gases, remember, so-called because they are unreactive and typically are found in the elemental form in nature. They don't react with other elements. They are stable. All right, so let's just quickly write the electron configuration for a few noble gases. We'll just do helium, neon, and argon. And I'm going to do this fast. Okay. 1s2, this would be 1s2, 2s2, 2p6. This would be 1s2, 2s2, 2p6, 3s2, 3p6. Okay, that's an S. March the 16th there. All right, so just taking a look at the electron configuration for the first 3 noble gases. We could write it for all the rest, but then we're going to have to deal with the d orbitals, which I doubt you'll need to worry about too much in an introductory chemistry class, so we'll just stop here. Okay, so what we see when we write these electron configurations for our noble gases is that the outermost energy level, the valence shell, is full for all of the noble gases. So for helium, the outermost energy level is the first energy level, which only has an s sublevel, and an s sublevel is full with 2 electrons. Okay. For neon, the outermost energy level is energy level number 2, which has an s and a p sublevel. So the outermost energy level for neon is also full with 2 in the S and 6 in the P. So full with 8 electrons. Same thing for argon. Its outermost energy level is the 3rd energy level. The 3rd energy level has an S sublevel and a P sublevel. The S sublevel is full with 2 and the P is full with 6. So again, the valence shell, or the outermost energy level, is full with 8 electrons. That full energy level is what makes the noble gases stable. They don't want to gain any electrons because then they wouldn't have a full valence shell anymore. They don't want to lose any electrons from that full valence shell. They want to stay the way that they are. They have a stable electron configuration. They have what we call in chemistry octet, meaning full valence shell with 8 electrons, with the exception of helium, which is full with just 2. So remember that one. Okay, so all of your noble gases have octet. And because they have that full valence shell, they are unreactive. So I'm going to write here, unreactive due to their full and stable valence shell. Okay. All right, well, let's do the same thing, but for the alkali metals. Okay, so I'm just going to really quickly write the electron configuration for lithium, sodium, and potassium. I'm not going to write it for all of them because I think this will be enough to make the point. Lithium, sodium, and potassium. Okay, so lithium is 1s2, 2s1. Sodium is 1s2, 2s2, 2p6, 3s1. And potassium is 1s2, 2s2, 2p6, 3s2, and 3p6, and 4s1. Okay, notice the pattern here. All of your alkali metals are going to have a valence shell with just 1 electron, 1 valence electron. That's all they have. Okay, so let me circle it here. Outermost electron energy level is a 2nd here. Outermost energy level is a 3rd here. Outermost energy level is a 4th here. They all have 1 valence electron. Okay, and so your alkali metals are all going to be highly reactive. They all want to react by giving up that 1 valence electron so that they too can then simulate the electron configuration of the stable noble gases, which have a full valence shell. If they could just get rid of that 1 valence electron, they would be left with a full valence shell. Okay, octet. All right, so let me write here. That's why the alkali metals are highly reactive and give up 1 electron, their 1 valence electron. Okay, so I'm going to show you a little trick here. So you don't really even need to write the entire electron configuration to quickly and easily see how many valence electrons a particular atom has. All you have to do is look at the group number, okay? So all of your alkali metals are going to have one valence electron. What's the group number? 1. Okay, so the group number will tell you the number of valence electrons. Okay. All right, so you can quickly and easily look at the periodic table and tell that the alkali metals all have one valence electron, and therefore you can quickly and easily tell that all the alkali metals are going to want to react by giving up one valence electron and forming a 1+ charge. Okay, a little foreshadowing of things to come. All right, let's do one more example just to hopefully really reinforce this. Let's look at the halogens. Remember that that's group 7A. Okay, I'm just going to really quickly write the electron configuration for a few of the halogens. Let's do fluorine, chlorine. Let's just do fluorine and chlorine because I don't want this to get too long. Okay, so fluorine is going to be 1s2, 2s2, 2p5. Chlorine is going to be 1s2, 2s2, 2p6, 3s2, 3p5. Okay. All right, so you could keep writing it for the other halogens as well. What you're going to find is that all of your halogens have 7 valence electrons, 2 in their outermost s and 5 in their outermost p. Okay. And of course, you could have gotten that from the group number. The halogens are group 7. All of your halogens are going to have 7 valence electrons, 2 in their outermost s and 5 in their outermost p. Okay? So not surprising, all of your halogens are going to be highly reactive as well. They want to react by gaining an electron and filling up that outermost shell so that they too will have octet. Okay, that stable noble gas electron configuration. So I'm going to write that here. Your halogens are highly reactive and gain an electron to fill their valence shell and achieve octet. Write that in parentheses there. All right. Okay, so I hope I've proven to you that understanding the electron configuration can go a long way toward helping you understand the reactivity of the elements. But in truth, the shorthand is just looking at the group number. All of the halogens are in group number 7, so they have 7 valence electrons. If all of your atoms' goal is to achieve octet, full valence shell of 2 in the s, 6 in the p, or 8 octet, meaning 8 valence electrons, then it makes sense that all of your halogens are going to want to react by gaining one more electron. Okay? So that will conclude our tutorial number 4, and I hope you will consider tuning into problem set 4 while I will work lots and lots of problems and write lots of electron configurations out for you to give you more practice with this. Thank you.